So my name is Piotr Sawicki. I work as a software engineer at Samsung R&D Institute Poland. And today I'm going to talk about the application provisioning mechanism that we have implemented recently in the scope of the Islet project. And before we begin, I have one technical note regarding the questions. I would prefer to take them at the end of the presentation. And the agenda for today's talk is as follows. Firstly, in the introduction, I will briefly talk about the Islet project and our main goals and key ideas behind the application provisioning design. After that, I will provide a high-level description of the provisioning architecture. Next, we will go through an example provisioning process, which help us better understand how it works. And finally, the last 2 points, namely the realm metadata and scenic key derivation, will cover our custom extension that we have implemented for the Islet RMM. Okay, so let's begin with a quick overview of the Islet project. So Islet is a project that enables confidential computing on platforms that support ARM CCA. These are platforms equipped with CPU cores implementing RV9 architecture with additional realm management extensions. And the main components of Islet are the Islet realm management monitor that currently implements the RMM specification version 1.0-EAC5. And our Islet RMM handles such things like virtual CPU context switching and stage 2 translation tables for confidential virtual machines. These are referred as realms, and it also provides API for realms, such as the API for retrieval of the attestation evidence. The other core component is the hardware for security module. It acts as a root of trust for attestation and plays a supportive role by providing secrets to Islet RMM. And both components are written in Rust. And on top of our firmware stack, we develop functionality that is going to be used on end-user devices because we are mainly interested in so-called on-device confidential computing. Okay. So now let's move to the main topic of today's presentation. So the main goal of our recent work was to implement a mechanism enabling provisioning confidential applications into realm virtual machines from some external application registries. As I said earlier, we are focusing on on-device usage, which means that we mainly target platforms like mobile devices and smart TVs. And you want to take advantage of the ARM CCA on these platforms. So in this case, you'd like to be able to install confidential applications on demand, similarly as regular applications running in the non-secure world, and then utilize them for performing computational tasks that require protection of data in use. One of use cases could be running a proprietary machine learning model as a confidential application inside a realm. In this scenario, the applications running in the non-secure world could use that model for their purposes. The next important goal was to support offline mode, which means that once an application is provisioned into a realm, it should be saved into persistent secure storage for later use. So in that case, if the realm is restarted, the application can be launched from its persistent storage without the need of reprovisioning. And additionally, applications should be able to save their data produced or downloaded in runtime. The last requirement was that our solution should target Linux-based environments. This way, in the future, we could easily port it to Android or Tizen operating systems. Okay. And here are the main key ideas behind our design. So firstly, the realm content is split into 2 parts. One is a base realm image that provides a lightweight Linux operating system running inside a realm VM. This operating OS serves as a host for provisioned applications. It contains a dedicated service responsible for the provisioning process. We call the service realm daemon. And the base realm image is kept in plain on the host side. And of course, in context of confidential computing, when it is launched, its memory content is measured to reflect the initial state of the realm in the attestation evidence. And the second part refers to confidential applications that are provisioned into the running base operating system. We have chosen the OCA standards for packaging the applications. It allows us to deploy applications ranging from lightweight to complex ones, containing multiple libraries and additional services. And of course, the provisioning process has to involve the remote attestation of the platform and the base RAM content. Here we utilize our custom implementation of the RATLS protocol that combines remote attestation and TLS. This protocol is used to establish a secure channel between the realm daemon running inside a base realm OS and an external image registry. In this case, the external image registry takes the role of a relying party in RAT's architecture, and the realm and the underlying platform take the role of the attester. To support the offline mode, the applications and their data are stored in encrypted disk partitions kept on the host side. They are attached to a realm virtual machine via the virtual interface. What is important here is that data encryption keys are bound to the platform, firmware, and realm content, effectively implementing the concept of sealing keys. Okay. And here we have a diagram that depicts the high-level architecture of our solution. On the left side, we have our device. On the right side, we have external entities, such as the image registry that keeps the repository of confidential applications. The registry interacts with an external attestation evidence verifier. In our case, we utilize the Verizon project. It is worth to mention that our solution could also work with the VMware certified framework for confidential computing. We have an SDK that provides support for it. On the device side, we have depicted two parts, the host and the realm world. On the host side, we have our Varden daemon, which is responsible for setup of realms, including the initialization of application disk images, network configuration, and initiation of the application provisioning process. The Varden daemon exposes a management interface to client applications running on the host side. So in the future, this will be Android or Tizen apps. Currently, for experimentation and development purposes, we utilize a command line tool that acts as a client. As a realm guest, we run our base realm image that provides a lightweight Linux OS together with the realm daemon. And the realm daemon is responsible for the actual provisioning process. It takes care of a setup of secure storage, downloading, verification, and launching of confidential applications. And at the bottom of this diagram, we have our core components, namely the Islet RMM and our hardware enforced security module. These components, apart from providing security to the whole CCA stack, produce attestation evidence and sealing keys required for secure storage. Okay, and now let's dive into the example of the provisioning process. Here, the Varden daemon launches realm VM using a previously prepared configuration. Basically, it loads the base realm image containing our custom Linux distribution with an attached newly created empty disk image. After the guest Linux boots, the realm daemon is launched, and during its initialization, it retrieves the sealing key from the Islet RMM. This key will be used in further key derivations. Then the realm daemon establishes a connection to the Varden daemon through the virtual socket interface to inform that it is ready to receive a provisioning request. After receiving the provisioning request, the realm daemon setups the application image partition. Then the realm daemon establishes a secure array TLS channel with the image registry. And this process involves remote attestation of the platform and the realm content. And the evaluation of the attestation evidence is done by the Verizon verification service. And when the secure channel is successfully established, the application image is downloaded and its authenticity and integrity are checked. And after successful verification of the image, the application's content is extracted into the application image partition. Next, the RAM daemon sets up the application data partition. It will be used by the application to store its runtime data. Next, to make a unified view of the file system for the application, an overlay FS is configured on top of the image and data partitions. And here we have a detailed view of the overlay FS setup. The application image is used as a read-only partition and the application data as a read-write partition. Of course, both partitions are encrypted using the Linux dmcrypt subsystem. And right before launching the application, a selected run extensible measurement slot is updated using the measurement calculated from the application. This step is needed to reflect the current state of the run in the attestation evidence. And finally, the application is launched. And when the application is running, it also can be provisioned with confidential data. And in the process that requires remote attestation. Okay. So the next points will be about our custom extensions that we had to implement for our realm management monitor. So the first one is the realm metadata mechanism. This is basically a cryptographically signed structure that provides identity, authority, and versioning information about a particular realm. Currently, it is used in the sealing key derivation process to produce stable keys that are immune to realm updates. And the realm metadata can also be used to implement a verified boot process of a realm image. This functionality might be important on mobile platforms where we want to have greater control on what is actually launched as a base realm image. And the second extension is the sealing key derivation mechanism. It is also currently missing in the RMM specification. Now we'll briefly explain how it works. So firstly, during the startup of the platform, the hardware-enforced security module gathers measurements of the Islet RMM and other firmware components. And these measurements, the security lifecycle state and the hardware unique key, are used as an input key material to derive two keys. The first one is the measurement-based virtual hardware unique key that is bound to the exact binary measurements of the firmware. And the second one is the authority-based virtual hardware unique key. That is bound to the verified boot authority and identity of the firmware components. Next, when the Islet RMM is initialized, it retrieves both the virtual hardware unique keys. And during the initialization process of realm, Islet RMM measures the realm's content. And when it is about to launch the realm, it checks if the realm initial measurement value calculated online is the same as that provided within the cryptographically signed realm metadata structure. In runtime, the services running in a realm, like for example the realm daemon, can fetch realm sealing keys from RMM. We have implemented an additional interface for that, which is fully customizable. For example, we can derive a key that is bound either to the measurements or identity data of a realm. And the services can perform further key derivation from the provided realm sealing key. In the case of realm daemon, it uses the application identity authority data to derive data encryption key that is bound to a particular application, realm, and a platform. Okay, and future work. We plan to harden the security of our solution, firstly by implementing a rollback protection mechanism. This will prevent from downgrading of applications and run images to older, possibly vulnerable versions. And this mechanism will require hardware support. For example, we will need a dedicated eMMC chip that implements a replay protected memory block to keep the versioning information. And other feature that we are interested in is the migration of confidential applications between end user devices. So basically, we'd like to handle a case when a user buys a new smartphone and wants to transfer all applications and data from the old device to the new one. And we have some initial thoughts about how it can be done. So we will probably need to perform a mutual remote attestation of both the source and destination devices. This process will require assistance of some external migration agent that acts as a relying party in ROT's architecture. And we think that this process also will require end-to-end encryption to be able to securely transfer applications and data from the source to the destination device. And this was my last slide. Thank you for your attention. Do you have any questions?
I think Fritz had a question. I don't know if you still have a question, Fritz.
Yeah, you partially responded to it a little bit in the last slide, but can you elaborate a little bit more on the ceiling? So, yeah, Dan also had one. So let me just try to bundle the all of them in one block. So, you did mention that kind of rollback attacks are not there yet, but you did mention that it could be a future work to add that with some hardware, right? So,
Yes.
and you derive the keys in the beginning from your hash, right? So that I think is also then responding a little bit to Dan's question. But can you say a little bit more about client devices? And so, is it a realistic assumption for your future work that you have this replay protected memory available, or what would you have to do on client devices? Future client devices that is realistic to achieve that. And then I also had a little bit side question, whether it uses AES XTS or what you use, because you also want authenticity, I guess, from the realm, right? It's not enough to just have integrity.
Yes. So maybe I will answer the last question. Currently, we are using AES. It's CTS, but we will probably it's configurable, and we'll use AES XTS, and also we plan to enable DM Verity to provide the mechanism that protects the data from sorry, it enables the integrity checks for in the DM encrypted partitions. And when it comes to the first question, basically we don't have hardware yet, but because ARM-CCA, what we use emulator to run the whole stack currently, and probably in the future we plan to maybe not design, but be involved in the design of the hardware of the target hardware, which will be used to on mobile devices, and that provides this replay protected memory block memory.
Thanks. I see. But so that can also so I have I think a good picture of what you could use there, right? You have all of these shenanigans you can do for monotonic counters. You can have
Yes,
extra
yes,
hardware,
I know.
etc.
Mhm.
But so what I was trying to, because I don't know anything about client devices. So what is hard for me to estimate is how expensive are those? And is it realistic to even put them on a smartphone, or because this is for client devices, the idea, right? So will this be so expensive that it's not only be realistic on the top
I think
end,
it's
or
it's
is it
realistic
fine?
because currently I don't know, TV sets are equipped with eMMC hardware that support the RPMB protection. So I think it's realistic.
Interesting. So the limitation is maybe like only a few realms for cheaper devices, and then larger devices have
Okay.
more realms or something. But then I guess you can have this on all the ranges, is what you're saying.
As far as I know, currently smart TV sets are equipped with such a memory, with authenticated memory. So basically, that implements this rapidly protected memory block.
Oh, interesting. Thanks. Cool.
Okay. Do you have another?
Maybe you've answered this, so sorry if this is not a great question, but the ceiling here, this is something that you've added as part of Islet, or ceiling is a built-in feature of CCA?
No. Not, actually, we had to add it to Islet. We have designed all this mechanism this year. So there is in the ARM CCA. I don't remember the name of the title of this document, but there is one document that mentions that it is possible to implement keys that would be used for derivation of disk encryption keys. But the current RMM specification doesn't provide such a mechanism. So we had to implement it.
Okay, thank you.
Thank you very much.
Any other questions for Piotr? And I'm trying to think, were there some specific things that your community wanted feedback from the TAC on? I think when Bokduk first reached out to schedule this, I think there were some open questions that maybe there was an interest in some best practices for.
Maybe we are interested in maybe you will provide us some, I don't know, you will point us to some projects that utilize similar technologies like this sealing key mechanism or data encryption, because when it comes to this security hardening task, we'd like to make some investigation about the other technologies that uses the same or similar mechanisms. So is it possible or not?
Say again the question part of that.
Maybe we would like to know if there are some projects which utilize a similar mechanism like this one implemented in our, like this sealing key derivation.
Okay, is anybody on the call? Does that ring a bell for anybody? Anybody familiar with the project that Isla?
Yeah, Ijlal here from Ubuntu. As you're presenting, Piotr, I'm seeing so many similarities with the ongoing work we have to make Ubuntu core confidential computing ready. And confidential Ubuntu Core is an immutable OS targeted for IoT devices. The applications, we provision them not as OCI images, but as snaps, which are just, an application with all of its dependencies, basically.
Okay. That's
So I
interesting.
would very much like to connect you with the people working on that project. There must be some learnings across both teams that we can take from each other. And the ceiling conversation was super interesting because we're struggling with that, and some of the assumptions we're making about that working would depend on hardware. So yeah, that's it's good to see that there is hope in that being available at some point in time.
Okay, thank you for that information. It's interesting.
And you said it was something core. I missed that.
It's Ubuntu Core. It's another offering of Ubuntu. Ubuntu Classic, we call it. It's what everybody runs on desktops and servers. And Core is the distribution of Ubuntu that is targeted at IoTs as an immutable distribution. We have DM Verity, by the way, as well. We have full disk encryption, TPM back to all that good stuff.
Oh, nice. That's nice.
All right. What's a great connection to have made here? Any other questions or comments for Piotr? All right, I think we are ready to move on then.